Kia ora and welcome back. In this video we're going to move on to our next topic, and that is looking at cyclic groups. We've already kind of met these. These are groups where you have an element A. Now we've talked about them in the context of them being subgroups, where essentially you form this set by taking an element from a group and then taking powers of it. Now it turns out that if you have a group that can be built this way, i.e. if you've got a group and you can find an element that takes in the role of the A that I've used here, then that group is called a cyclic group. Okay, so we won't really make much distinction between talking about a cyclic group or a cyclic subgroup of a regular group, but we're going to look at the structure of these things and what we can prove about them in particular, as opposed to groups in general. Because it turns out that the theory of cyclic groups has a really interesting and quite rich structure, and we'll enjoy exploring that. Alright, so let's dive straight into our definition. We say that G is a cyclic group if we can find an element A in G, that's this one here, so that if we take powers of A and collect them all into a set, and that gives us the entire group, then we say the group is cyclic, and the element A is called a generator of our group G. Okay, and we also write that G is equal to, and you put some angle brackets around A, and that's our notation for writing a cyclic group. So we'll often just refer to a cyclic group just by using simply this notation here and be done with it. Okay, so let's look at a couple of examples just to put this into a wee bit of context to start with. So let's look at one from the integers first. If we look at the integers under addition, these are cyclic because, if we think about it for a second, if we're asking whether or not a group is cyclic, we're saying, is it possible for us to find a generator for that group? So for the integers, the generator is 1, or one of them is. So we could write z equals 1. Okay, so remember when I'm taking a to the n, if we're in a group using additive notation, like the integers are, then that is the set of n times 1, where n is an integer. Don't forget the definition includes negative integers as well. So z is equal to a cyclic group generated by 1. And it's also equal to the cyclic group generated by negative 1, because it works the same way. So z has two generators, 1 and negative 1, and no others. You can check that for yourselves. But z is therefore cyclic. Likewise, if I look at Zn, also cyclic, because I can take 1 to be a generator. Okay, so just remember how that works. We're going to add 1. If I keep adding 1, let's just say we're in Zn, we get as far as n minus 1. I'll add 1 more time and I'll get back to 0. And then I'll start my sequence again. So Zn is cyclic, and it's also generated again by minus 1, which for Zn is the same thing as n minus 1. Okay, so let's look at Z6, just to see how that works. Now we're not going to do anything clever here, we're just going to literally try each element out and see if it's a generator. Because there may be more than 1 and negative 1, or sorry, n minus 1, which for us will be 5. But let's see. So, let's take the cyclic subgroup of Z6 generated by 1. We know that will be our entire set, so I'm just going to take 1 and keep adding it mod 6 until I get back to where I start. Okay, if I were to keep adding 1s, I'd cycle back around again. That's kind of why it's called cyclic. So let's give it a tick, because it is a generator. Is 2 a generator? Well, again, we can I'll start with 0. Add 2, add 4, add 2 again gets 4, add 2 again gets 6, which is back to 0. So 2 is not a generator. Let's put it here. What about 3? You can probably see where this is going. 0, add 3 is 3, add 3 is 6, which is back to 0. So 3 is not a generator. What about 4? Well, it's only going to give us even numbers when we add, so we're going to guess that's a no. Add 4 is 8, which is 2, mod 6. Add 4 again is back to 0. So for Z6, the only ones we have are 1 and n minus 1, which is 5. Good to actually see if that actually works, because I've just kind of told you it does. Let's see. Well, we'll start with 0. add 5, we'll get 5. Add 5 again, we'll get 10, which is 4. Add 5, we'll get 9, which is 3 mod 6. Add 5, we'll get 8, which is 2 mod 6. Add 5, we'll get 7, which is 1 mod 6. Add 5 again, and we'll get back to where we started. So Z6 is generated by both 1 and 5, and nothing else, because we tried everything. Well, I suppose for completion we should try 0, and that's just going to be 0. Okay, now not just integer groups are cyclic, so let's just check a couple more. U of 10 is cyclic. Why is that? Well, when we looked at the cyclic subgroups of it, we saw that this thing is, now we're multiplying mod 10, so we get 3 times 3 is 9, times 3 is 27, which is 7 mod 10, times 3 is 21, times 3 is back to 3. Okay? So we can have cyclic groups that don't look like integer ones, but U of 8 is not cyclic. So remember, U of 8 is just the set of numbers relatively prime to 8, so it's going to be 1, 3, 5, and 7. So let's just try each of the elements. We know 1 is not a generator because it's the identity. 3 equals 3 squared is 9, which is 1 mod 8, times 3 is 3, so back to where we started. We can check each of these entries, and we're going to find they all have order 2. Okay, 5 squared, so we'll start with 5. 5 squared is 25, which is 1 mod 8, because it's 1 more than 24. 7 squared is 49, which is 1 more than 48. So all of these other three things generate cyclic subgroups of order 2. None of the entries are generators of the entire group, so U of 8 is not cyclic. So we can't say anything general about our U groups being cyclic or not, because some of them are, some of them aren't. It really depends. Okay, so we're going to move on and start looking at some of the theory involving cyclic groups, because there are some quite interesting things that we can say. Okay, so let's take a look at proving this thing. Here's our theorem. The theorem is about whether or not a to the I is equal to a to the j. So basically the answer to that question depends on whether we have a group with infinite order or whether we have a group where the element has finite order. So the theorem reads, let G be a group with A being a member of G. If the element A has infinite order, then a to the I equals a to the j means that I equals j. So they're equivalent statements. Notice we're talking about any group here. We're not just talking about cyclic groups at the moment. Okay, so if A has infinite order, that means there's no n, so that a to the n is the identity. Then a to the I equals a to the j. The only way this can be true is if I equals j. But if the order of A is n, then the cyclic subgroup generated by A is precisely this set here, so that's something we need to prove. At the moment, our definition of cyclic group just means all integer powers of A, so we need to show that it's restricted to that set. And additionally, a to the I equals a to the j doesn't just mean I equals j, it means that n divides I minus j, which is a slightly different statement. Okay, so let's see how we go. So I want to prove this thing. So we're going to have to attack the different pieces separately. The first piece is we've got a group with an element A of infinite order. So we're going to look at this bit first. Okay, so A having infinite order, what does that mean? So remember, every piece of information in the theorem statement is probably there for a reason. So if A has infinite order, the mathematical way of writing that, then there is no non-zero n such that a to the n is the identity. Okay, so remember the order of an element is just the smallest positive integer n that gets you to the identity when you take a to the power of n. But if a has infinite order, then there are none of those n's. Okay, so that's the mathematical way of writing down the information that we've been given here. So now we need to establish that a to the I equals a to the j if and only if I equals j. And all we need to break this is some kind of counterexample. So we will suppose that a to the I equals a to the j. Right, then this implies we can multiply both sides by a to the minus j. A to the I minus j equals e. And hence I minus j equals 0. Okay, that's interesting. So if a to the I equals a to the j, then this directly implies, i.e. a to the I equals a to the j implies I equals j. Okay, and the other direction, so we've proven one direction of our if and only if. The other way, now when I say one direction, I mean that we've started from the first statement here, and I've shown that it implies this one. When we have an if and only if statement like this though, we also have to imply the other one. So if I equals j, then a to the I equals a to the j. There's really not a huge amount to say here because that's true by definition. If I equals j, then clearly a to the I is equal to a to the j. There's not much to say there. Okay, so we've actually proven our first part, just sort of popped out there nicely. So a to the I equals a to the j if and only if I equals j. Now for the second part, we'll now suppose that the order of a is equal to n. Okay, so we need to show that A, the cyclic subgroup generated by A, is equal to the set that was provided. Okay, precisely these elements here and none other. Okay, now, how do we do this? Well, remember our definition. We just scribble in some space down here. Our definition says that this thing is equal to the set of all a to the n for integer n. So essentially we've got to show that any other integer other than those 0 up to n minus 1 will just give us something in this set anyway. Okay, so we will suppose that a to the k is a member of our cyclic subgroup, where k can be any integer, and what we'll do is we'll show that it's equivalent to one of these n entries. And the clever trick for doing this is to use the division algorithm. The division algorithm is something that's really useful for often resetting an infinite integer into one between 0 and n. So then by the division algorithm, this k is equal to qn plus r for some q and z and some q and r and z, where in particular r is between 0 and n, not including n. Just tidy that up slightly. Okay, so division algorithm, the key part of the division algorithm is usually the fact that we're starting with our k, and often the aim is to turn it into this r and show that it can equivalently be used as this r here. So in this particular context, how's that going to work? Well, then a to the k is equal to a to the qn plus r, which is equal to a to the qn, a to the r, which equals, in turn, well, a to the qn, that's just q times the order of a, so that's just the identity, so it's just e to the q times a to the r, which just equals a to the r, which is a member of our set. Okay, so if we take anything outside of our set, then we can use the division algorithm to show that it's equivalent to something inside our set. So this says that this is actually the correct set of elements to be a cyclic group. Okay, now we're going to have to attack the if and only if proof. Assume that a to the I is equal to a to the j. Then a to the I minus j equals e, and hence there exist Q and R again. I'm going to make some new ones because it's always useful. Q and R and Z, where such that I minus j equals Q n plus R, and R is between 0 and n. So again, I'm using the division algorithm to get the property I want. This time I'm using it on I minus j, because it will again get rid of anything, or it will come up with a number of a to the n's, which will just go away because they're identities, and we'll show that it's equivalent. We'll show that R will have to be 0 here. So a to the I minus j equals a Qn plus R equals a to the R, because we did that before, equals the identity. And the only way this can be true is if R equals 0 as R is less than n. The only way that a to the R can be equal to that entity is if R is either 0 or a multiple of the order of A. The order of A is n, and R is less than n, therefore R has to be 0. Okay, and what do we conclude from that? And therefore, if we go back to our statement, we've now shown that I should have been I minus j up here, apologies. I minus j equals Qn, i.e. n divides I minus j. Okay. The last thing we have to do is to then show that the other way holds as well. So suppose n divides I minus j, which means that i.e. I minus j equals Qn for some q. And we need to show, so we're attacking this statement here. We've shown this direction already. We're now attempting to show the opposite. So I'm assuming that n divides I minus j, and I need to demonstrate that a to the I equals a to the j. Once I've done that, I've put all the pieces together and I've proven the entire theorem. So I've said, all right, suppose that n divides I minus j, so I'm assuming this part. What happens, can I show a to the I equals a to the j? So I've said n divides I minus j, and I've set that up as a statement about some integer q existing such that I minus j is a multiple of n. And now I just need to produce a to the I equals a to the j from that somehow. Okay, so if I just take this and take a to the power of each side of that expression, so hence a to the I minus j equals a to the qn equals e. And then if I multiply both sides by a to the j, I'll get a to the I is equal to a to the j as required. Okay, and at this point, we have proven our entire theorem. Okay, we've shown both directions of both if and only ifs, and therefore we have our statement about when it is that a to the I can equal a to the j. Okay, so that was just a kind of preliminary theorem that we needed to get out of the road, because we need to be pretty clear about when it is that a to the I equals a to the j, because we can get a little bit muddled up and be tempted to draw the conclusion of the infinite order case that if a to the I equals a to the j, then the exponents must be equal, because that's what we get in regular calculus with exponential function and that kind of thing. But here, if we have finite order elements, it means that I minus j differ by a multiple of n, so it's not quite the same thing. Right, I think we've gone long enough for one video. So next time we'll start looking at some more theorems about cyclic groups and some corollaries to this one here. Until then, ka kite anō.